Okay, so today I will tell you about some work that was done in our team in Dublin to secure machine learning. So far, most of you have probably seen machine learning applied to security tasks with more or less success, and it has been controversial, maybe for this reason as well. Because maybe machine learning has been taken for granted and taken as a miracle solution, and well, it isn't. But today what I will tell you about is how things work the other way around. That is, what can we do in security for machine learning. So moving back to a bit of a background in machine learning. So in machine learning, what you're trying to do is have a prediction model which is able to solve a certain task. Now, the way to build that prediction model is through a training step, in which you would show your model the data that it's expected to receive. In this case, the example is with, for example, pictures, and what you would expect it to predict, the correct output, right? So, for example, in a task of visual recognition, you would feed it pictures, and you would expect the correct answer to be what is the object that's present in the picture. Now, once you've done the training step, you have your prediction model that can be then used in a real-world setup where you would feed it inputs, and you would expect it to predict the correct output. Now, when you set this kind of model up in the real world, let's say, many things can happen. So you most likely will have your data storage that you will be using for training. And then going for a training step, obtain your prediction model that we've talked about, and then this prediction model will interact with whatever clients you have or exterior, right, to make those predictions. But again, the system can be hacked on a lot of levels. This is by no means a complete list, but these are some examples. So for example, when we speak about the data storage, you might have client data, so then it should remain private, it should not be leaked, right? In the same way, if you have personal information, you should be able to ensure privacy. At the training step, what can happen is, if an adversary of an attacker has managed not only to read the data you have stored, but to tamper with it, to change it, right? This will affect your training procedure. So, for example, think about the crowdsourcing, think about whatever you would use from user reviews to train your model on. These should be curated on one hand, and on the other hand, again, for personal information, you should be using differential privacy and anonymization of the data on one hand, and on the other hand, your AI in itself, your machine learning model, might be intellectual property to the company you're working in, and this should not be leaked either. In the sense that by querying it, inputs and outputs, you risk on basically leaking your model. Now, when the model is already trained and, let's say, in production, something else can happen. Of course, you can bombard the system with queries, and then you can get into attacks like denial of service or stuff like that. But there are some specific attacks to machine learning models, and this will be a topic for our talk today. So one way to protect against this would be to use some model hardening techniques, and again, this is what we will be looking into today. But some other way would be to, for example, add kind of a detection system in order to detect intruders or anomalies between your prediction model and your outside. So, more into our topic for today, adversarial examples. So these are a type of attack that can be used on prediction models and is specific to prediction models. Once they have been trained and you are trying to use them. So now what you have here, well, is maybe the case of images is the best example for the visual, for our visual capacities as well. So consider this case where you would have the picture of a giant panda, which is recognized correctly by the model, and and with a confidence score which is pretty high, 84%. Now, to this image, you're adding this noise, and what you obtain in the end is an image that to us looks exactly the same as the original. But it will be able to fool the model into thinking that it's actually a monkey. For us, it still looks like a panda, and it's a monkey with pretty high confidence as well. Now, of course, so this noise is undetectable by us, and a second problem is that, or not, maybe not a problem, this does not work with random noise. So the noise you have here in the middle is not random, but it has been engineered in such a way to make the model fail. So why is this important? Well, let's say many people are hopeful these days about self-driving cars. This is an example that was done for the task of image segmentation, right? So you have a camera, I don't know if you see it, but this is like the top of the hood of a car. The camera is on top of the car and filming outside. This is the original input where the camera is able to recognize the red class as being pedestrians. Here is the perturbed image, which looks mostly the same, but now the same model is unable to detect pedestrians anymore. Now, of course, this is a liability, right? In the same way, kind of for the same problem, if you want to do road signs recognition, here, well, basically you can almost tell just a bit that the images are not exactly the same, but I'm not sure you can tell which one's the clean one and which one is the attack image. So the first one will be recognized as a stop sign, but the second one will not. To get out of the image range, there are also examples. This was presented last week in CCS. They are able to attack all these voice assistants with commands that you cannot hear, and they were making Alexa order stuff on Amazon and all that. So this problem of adversarial examples is true for all machine learning algorithms, but maybe even worse in the case of deep learning. So neural networks are a type of machine learning algorithm. And well, from the point of view of the user, you can just see them as a black box, right? That just you feed inputs into it, and you are happy that you're getting most of the time the correct input. But now let's look a bit into what happens inside. So again, I will be using the example of feeding images through the system and trying to predict what object is present in that picture. So neural nets are made of, well, neurons, some units that are called neurons, which are organized by layers. And the layers are stacked together, and basically they transport and transform the input forward into obtaining the correct output. Basically, these are just mathematical functions that are composed. And when you feed it an input, for the case of the image, what you will have is that your number of neurons in the input will be the same as the number of pixels in the image. So basically, each neuron here gets the level of color for 1 pixel, and then the information moves forward through the layers. And at the level of the output, you will have as many neurons as possible outputs. So for example, if you're able to recognize 10,000 different objects, you'll have 10,000 output nodes, and the correct prediction will be the one that obtains the highest score here. So if the giant panda has the highest score, it is considered to be that one the correct prediction. Now, when you feed it the adversarial input, again, we do not detect the visual difference, but of course the values in pixels have changed, and when that information is propagated forward for all the connections, basically that changes as well the value of the output, and kind of it has a cumulative effect as the information moves forward through the layers. So now the maximum class is not, value is not the giant panda anymore, but it's going to be, well, in this case, monkeys. Now, this feature, well, this is actually a feature of neural nets in the sense that this is what will allow them to make the distinction and be able to discriminate between, for example, different types of dogs, right? I mean, they're probably able to recognize more types of dogs than I am able to. So, but on the other hand, this is also what makes them vulnerable to attack. So in order to maybe understand things a bit better, let's take a look at how the model sees the world, let's say. The model has kind of an internal representation of the world, which allows it to discriminate between different categories of objects. So here I've taken a simplified example. Let's say we're not trying to recognize 10,000 different objects, we're only trying to recognize two types. The yellow crosses against the orange ones. Right? So what you have, like the x's, are the training data. So this is what the model has seen of the world. And the background colors in yellow and orange are the true distribution of the data. Those are basically the valid points, the valid inputs for the model can come from those regions, even if you haven't seen them in training. And here, the model will be the red line, which, according to the data we have seen in training, according to the crosses, is able to well separate the yellow and the orange x's. But if you take a look, with respect to the true data distribution, the model doesn't match it perfectly. So this is what creates the space for adversarial examples. This is where adversarial examples will exist. So basically they will be valid, let's say orange inputs, but by the model they will be considered on the yellow side. Now this is again a very simplified case because we're only considering here two types of objects, and this is a 2D representation. Normally, for example, neural nets use a representation with hundreds of dimensions, at least. Now, as I was saying earlier, random noise, because we're in high dimensional spaces, random noise does not work well to generate adversarial examples. But what works well is, starting from a valid input and trying to explicitly move it across the boundary, the decision boundary of the model into a different class. So this is done by all of these attack methods. They all use kind of the same principle, which is in order to compute this exactly orthogonal direction to the decision and move the points over, they use more information about the model. So they need to have access to the network and its parameters to be able to compute this. And basically, yeah, they start with a valid input, and they only now add the missing noise in order to move the examples over. So all these methods use the same idea, and then they're only different in heuristics and approximations they make. So now the idea for to defend against this type of an attack was to integrate this anomalous inputs into the training data. So if the model has seen it before, and you have told them that they're supposed to be recognized as this class and not this other class, it will most likely adapt to that. So we're trying to adapt the model to that. That is the case of adversarial training. And so for that, the procedure is to, of course, first of all have a trained model, then generate your attack, and then completely retrain your model on all of your regular data plus the attack samples. And you can do this, this is basically attack dependent, right? Because you will be generating your samples according to some attack method. And there are other types of defenses, basically more related to pre-processing. So for example, feature squeezing, what it does is that you are reducing, for example, in the case of images, you reduce the bit depth, the color depth. So basically, instead of encoding your colors on 32 bits, you code them on 3 bits, right? But then, of course, there's loss of information, and then also your machine learning model will perform worse. And something that's similar about the label smoothing. So once you incorporate in adversarial training, you incorporate the new data, the adversarial inputs, the model will adapt to that. But of course, you're in high-dimensional spaces, so it will only adapt to the sample that it has seen. You are unable to explore all the possible things that can go wrong and all the possible adversarial examples. Which brings me to our contribution. So what we were trying to do is to make the model robust to these adversarial examples, but without necessarily having to go through that extra cost of applying an attack that would only make the model robust to that attack and having to retraining. I mean, training machine learning models, depending on the size of the data, can be kind of a lengthy process, so you want to avoid having to do it twice. So our idea was to, instead of integrating adversarial examples into the training sample, we would just take regular clean inputs and perturb them with Gaussian noise and create, let's say, 10, 20 versions of the same image with the same correct label and feed all of that into the model. Now, the second problem I was telling you about is the fact that as the information moves forward through the layers in the network, errors start to accumulate layer after layer. Now, one of the reasons for that is that each neuron has what is called an activation function. So basically, this is kind of a filter which moves the information forward to the next layer in some way. So this is randomly is one of the most used activation functions. So what it does is just filters out the negative values and it moves the positive ones the same way into the next layer. But of course, as you can see, this is a function that goes to plus infinity. So this is exactly what allows errors to accumulate, right? So for this, what we were thinking is, what if we bounded this value, and basically your function would have kind of a saturation point. So basically, information, I mean, you're still activating that function, but it can only activate up to some point and not to retake. So by combining these two heuristics, that is Gaussian data augmentation, and doing this numerical change in the activations in the layer, we obtained a new defense against adversarial attacks. And now I will present some experimental results we had. So we were using two data sets, which are fairly standard in machine learning. MNIST, this is our just handwritten digits, and CFAR, which are small images. They're all in the order, in the range of 60,000 images, and with 10 different categories to recognize. This type of architecture we were using for the neural net is what is called a convolutional network, which is pretty, well, it's a standard for visual recognition. Now, as I was telling you earlier, in the case of attacks, the attacker needs to have access to the model, to the actual deep neural network, in order to produce a good attack, to perform the attack. So that would be the case of white box attacks, where basically the attacker has access to inputs and outputs, and all the parameters of the model. But then, of course, if the model is properly secured, the adversary would not necessarily have access to that, and then we're in a black box setting. Now, what's interesting for the black box, where the attacker only has access to inputs and outputs, is that there is a transferability effect. That is, it has been found that you do not need proper access to a neural net in order to be able to attack. What you can do is create a surrogate on your side using pretty much only common sense and similar data. So if I know I'm in the case of visual recognition, I will think that, well, most likely it's going to be a convolutional neural network, and I will train it on my side with my data and attack my model and use those attack images that I've obtained to attack a different system, right, for which I only have access through an API. And it turns out that this works pretty well. So I don't need access to the actual model, I only need access to a similar model to be able to attack. So now, for a visual inspection of what our method is able to do, here consider 10 clean samples of the MNIST data set. These are actually these are not selected, they are the first 10 samples of the data set. And then we have here 3 attacks and 2 columns for each. In the first column, you're going to have how the image looks, the original image looks after the attack. And in the second column, you're going to have how it looks when you're trying to attack the model with our defense in place. Now, For different reasons, the adversary might want to remain inconspicuous. But what you can see here is that in most cases, here the numbers were still looking valid, but after the attack, they are almost unreadable. So first of all, the adversary would be detected in this case by a human, let's say. And second of all, these are not valid inputs anymore. So basically, even if your prediction model fails, most likely a human would fail as well. You can't necessarily tell what numbers those are anymore. So this is the case for the first two attacks. The third one is still working pretty well, and it's still hard to detect it visually. And here we have some results for a white box attack. So what we have here is, this is the size of the perturbation, right? So, and here you have the accuracy of the model. Maximum is 100%, the higher the better. What you have here for 0 is the performance of the model without any perturbation, so that is on clean images. And we're comparing, we have two attacks. FGSM is one of the fastest methods, but not necessarily the most subtle. So think about this column here. And the random FGSM is using the same attack, but it's basically taking a random step that is applying a random perturbation to the image, and then applying the original attack. So here, the first method is just the convolutional neural network with no defenses. And then we have all the defenses that I mentioned earlier, and the Gaussian data augmentation with the rally activation function, or the bounded rally activation functions are somewhere around here. I know these are many curves here, but what you can see is that there's only one curve that's obviously above the others, and that's the Gaussian data augmentation with bounded rally activation. What you can also see is that as perturbation increases, all models fail eventually. Now, for the case of black box attacks, we were comparing 5 different attack methods that were that were producing the adversarial examples in a transferable way. So that is, we were using a ResNet architecture, which is also a type of convolutional neural network. And then we were transferring those attack images to all these methods, basically, again, the convolutional neural network without any defenses, and then with all the defenses mentioned previously. So the best results, of course, here, the closer we get to 100%, the happier we are. And first two results, best results are in bold. So what you can see is that Gaussian data augmentation obtains the best results, the two best results in almost all cases, with the exception of random plus FGSM. Now, I cannot really demo how we would train a model and how would you train it for with a defense. But what I can show you is our proof of concept of how we can generate adversarial examples pretty quick. So we have this web interface where you can choose a type of machine learning model, let's say this one, and you would upload a clean image. This is from a standard dataset as well. And then you would choose the size of perturbation that you would want to introduce. Let's say this. And then you'll have to wait for a while. This is why I'm unable to show you how defenses work, because training models is extremely long. Even generating adversarial attacks is pretty long. Here, I'm using FGSM, which is one of the fastest attack methods. But on the other hand, is one of the least subtle. So you'll actually be able to kind of tell that there's some noise in the attack. And hopefully this will come back at some point. the original image, and what you can tell is that it has been recognized correctly and with 91% confidence. And this is the noise that was applied. And you can pretty much tell kind of this is where the bird would be, right? And this is the final image. So as I was telling you, you can actually tell that the image was tricked, but this is also because, so first of all, because the attack is not too subtle. It's fast, but not too subtle. Well, relatively fast. And second of all, because the perturbation I was using is pretty high. And you can see that now it is incorrectly recognized as a puzzle. Now there's one nice feature here. We have this, which is pretty much justifying the decision of the model to some extent, in a sense that you have this heat map showing where the model focuses when it's making this prediction. So basically, yeah, you can say that after the attack, the focus areas have changed, and yeah, the prediction is not correct anymore. So what we have done is we have proposed a new defense against adversarial examples, which performs well, I would say better than other defenses that were available so far. It hasn't solved fundamentally the problem of adversarial examples, but it has the advantages of being easy to integrate into a model. You do not need to be a machine learning expert to be able to produce Gaussian noise, right? It can be used in one pass. You don't have to retrain your model. And also on the original clean data, but it's not losing any of the information in the training set. It's not degrading performance either. Now maybe the takeaway for you is more related to the fact that machine learning should be secured properly, and this type of problems should be solved before actually using prediction models in the real world, especially when important decisions, say self-driving cars, national security applications are at stake. And we will be hopefully open sourcing very soon our library of attacks and defenses. So the attack and defenses that you've seen earlier. And if you want to read the full paper, it is available on archive. Now this project was a project in our team, and these are my co-workers that have also been working for these results.